All right, let's go ahead and talk about the inverse tangent function. So here's the graph of the tangent function without the vertical asymptotes, because they're going to kind of make things cluttery. So we'll ignore those for now. We'll get back to them later. So this is the graph of the tangent function without the vertical asymptotes. And we see that this graph does fail the horizontal line test pretty badly. So any horizontal line that we draw anywhere is going to intersect this graph infinitely many times. 5 times that we can see. But there's infinitely many more pieces of the tangent graph out here and out here, to the right and to the left. So what we can do is restrict this, restrict the graph here, just like we've been doing. So if we restrict that, let's restrict it to be between negative pi over 2 and positive pi over 2, and then we'll just be looking at this right here. Okay. So this graph of the restricted tangent function does pass the horizontal line test, because we see that any horizontal line that we draw is going to hit this graph once and only once, and that's fine. That means that this graph does pass the horizontal line test, so we can use it to get an inverse function, or at least the graph of one. So remember, if you want to get the graph of an inverse function, you take the graph of your function and reflect it over the line y equals x. So if we take this graph of our restricted tangent function, reflect over y equals x, we're going to get this graph right here. And let's take a look at that by itself. That is the graph of the inverse tangent function. And what's different about this as compared to the inverse cosine and inverse sine graphs, what's different about this is not the whole thing. It does keep going infinitely far to the left and infinitely far to the right. Okay, and the reason is that, remember when we took the graph of the restricted tangent function here, okay, we only restricted by cutting off pieces to the right and to the left. But this still goes infinitely far up and infinitely far down. Okay, so that when we reflect over the line y equals x, this piece here goes infinitely far to the left and infinitely far to the right. Okay, so this piece of the restricted tangent function goes infinitely far up and infinitely far down. So when we reflect it over y equals x, this piece here goes infinitely far to the right and infinitely far to the left. Okay, and another thing that we should point out, now let's go ahead and talk about the asymptotes. So with the vertical asymptotes, we did take them out, but if we go back through this, the graph of the restricted tangent function here is going to have a vertical asymptote at x equals negative pi over 2 and x equals positive pi over 2. Okay? And if we take those vertical asymptotes and reflect them over the line y equals x, we're going to have horizontal asymptotes. So if you take a vertical line, reflect over the line y equals x, that's going to give you a horizontal line. So x equals positive pi over 2, that vertical asymptote for the tangent graph gets reflected over y equals x, gets reflected to the horizontal line y equals positive pi over 2 for the inverse tangent graph. And the same thing, x equals negative pi over 2, that gets reflected over to y equals negative pi over 2. Okay, so here's the graph of the inverse tangent function by itself, and here's the graph with its horizontal asymptotes. So yes, the inverse tangent function, the graph, does have horizontal asymptotes. Here's one at y equals pi over 2, and another one at y equals negative pi over 2. So as x goes really far out to the right, all the way out to the right there, the graph is going to get infinitely closer to positive pi over 2, to y equals positive pi over 2, but never actually touch it. And if we go infinitely far out to the left, the graph is going to get closer and closer to y equals negative pi over 2, but never actually touch it. Okay, so again, the inverse tangent graph does have 2 horizontal asymptotes, y equals pi over 2 and y equals negative pi over 2. Okay, let's talk about some of the properties and how it relates to the tangent graph. Okay, so the domain, as we saw from the graph, remember the graph extends infinitely far to the left and to the right, so the domain is actually all real numbers. So you can take the inverse tangent of anything you want. Okay, that's kind of nice. There's no domain restrictions. But the range restriction, as we saw here in the graph, this is restricted to be between negative pi over 2 and positive pi over 2, non-inclusive, right? So negative pi over 2 is not actually a value in the range. Positive pi over 2 is not a value in the range because we have the horizontal asymptotes there. So that's why we have the rounded parentheses here. Okay, it's an open interval. It does not include the endpoints, so be careful about that. So again, the domain is all real numbers. That's nice. The range is from negative pi over 2 to positive pi over 2, not including the endpoints. Some notation. Y equals inverse tangent of x, or tangent inverse of x, negative 1 in the exponent there. And another way of saying that is arctan, y equals arctan of x. That's another way of saying the inverse tangent function. and short for arctan is atan. Not quite as common as it used to be, but I guess it just depends on where you are. Anyway, three different ways of saying exactly the same thing, just the inverse tangent function there. Okay? The inverse tangent of x denoted three different ways here. Really, they all say exactly the same thing. Some cancellation properties here. Inverse tangent of the tangent of x equals x if x is strictly between negative pi over 2 and positive pi over 2. Okay, so here, this is a strict inequality, so we're not allowed to have equals to, right? X cannot be equal to either of these, because if x is equal to these, then we have a domain violation. Okay, so we cannot take the tangent of pi over 2 or the tangent of negative pi over 2, right? So be careful about that. Now you might be wondering, what if x is outside of this interval? What if x is less than negative pi over 2 or greater than pi over 2? Well, then there are other ways of evaluating this, and we'll talk about that in a later video. Okay? All right, so what if we have tangent of tangent inverse of x? Well, that's going to equal x for all real x. That's really nice. Okay, so remember, the domain of the inverse tangent function is actually all real numbers. So tangent of the inverse tangent of x equals x for all real x. So that's actually really nice. There's no restrictions there. This is always going to be true for all real values of x. So that's great. That's wonderful. Really nice there. Okay, so that's pretty much it for the inverse tangent function. Just some quick notation, notes about the notation. So remember, y equals tangent inverse of x. This -1 in the exponent, we want to be very careful because it does not mean what it normally means for algebraic expressions. Inverse tangent of x is not the same thing as 1 over tangent of x. So usually this -1 in the exponent means do something like this, but for trig, it does not mean that. Be very careful about that. Inverse tangent of x is not the same thing as 1 over tangent of x. Okay, 1 over tangent of x, that's cotangent of x, and cotangent of x is not the same thing as the inverse tangent of x. So this notation just comes from the fact that if you have a function f of x, the inverse is denoted by this -1 in the exponent here in the superscript. F inverse of x is the inverse function for f of x. So if our f of x, if the function is tangent of x, then the inverse function is denoted like this, -1 in the exponents. Okay, so that's it for the inverse tangent function. The other inverse trig functions coming up in the next few videos, followed by some properties and examples of evaluating.